Welcome back, folks. Since I can teach from anywhere, I've decided I want to teach at Hogwarts. So there we go, just for the intro. I'm really in my basement. Anyhow, let's learn mesh analysis. All right, let's find these mesh currents because that's what we've got to do. We know how to use them. We can go find voltages. We can go find currents anywhere in the circuit that we need to once we know the mesh currents, but we got to go find the mesh currents. So let's work up to that. I have some steps that we can use for the first handful of problems, but I think I have a much better summary sheet. Look for it in the class notes, but it's a lot of information all at once. So I kind of want to start out with just these 5 steps and kind of build up the more complex things that we need to do. But in the end, it's very procedural. If you can read and understand that summary sheet at the end of this chapter, then you're going to be an expert at mesh analysis, and you're going to be able to analyze any circuit. Okay, so let's get down here, get rid of the castle. I got better castles than that. You'll see. Anyhow, so here are the steps for mesh analysis. We're going to start out with these, and they're all built off of Ohm's law, KVL, and KCL. The first thing we do when we look at a problem is assign the mesh currents. In the past 2 videos, I gave you the mesh currents, but those aren't going to be labeled. You get to pick them. Some decisions flow from how you pick them, but the schematics you pick up aren't going to have things labeled like that, so you have to pick them. We're then going to write a KVL around each mesh current, and in doing that, we're going to end up with the same number of equations that we have on knowns. Okay, then we'll have to figure out how to solve that, and there's going to be some other videos for you to watch on how to solve it using your calculator, how to solve it using MATLAB. Maybe I'll even throw out a Python video on how to solve it using Python. I think that'll be pretty cool. But right now I want to focus on how do we get the equations and how do we get them in a format that we can use for all of those tools. Okay, then go solve it using whatever tool you want. Maybe I'll even bring up the calculator. Maybe I'll show you the 84 on this one. Once you write the KVLs, you gotta rewrite the expressions in terms of the unknowns. Okay, we're trying to find currents, but we just wrote a bunch of equations with voltages. So we got to take those voltages and we got to convert them to currents. And we know how to do that because you watched the last 2 videos. You know how to use the mesh currents to find voltages. Okay, so we're going to use Ohm's law to do that. A little bit of algebra, and then solve it using whatever tool you want to solve it with. If you're going to go take the FE, make sure you're doing it on the calculator that you're going to use when you take the FE exam. Okay, so those are our steps. Let's get a problem to work with. It's a problem that we saw before. It was the last problem that I used when we were talking about the seat of the pants method of circuit analysis. And I believe the answer was 14 volts. And if we do mesh analysis correctly, we're going to get the same answer. We really want it to be consistent because we're not doing anything drastically different. All we're doing is applying KVL, KCL, and Ohm's law, but we're doing it in an organized fashion this time. Okay, let me get you a problem here. Same one as before. Okay, make a little room. And there it is. Does it look familiar? I hope it does. It means you've been watching my videos. And we want to go find VA, but this time we're going to use mesh analysis. All right, so step 1 says assign mesh currents. So I usually in front of the classroom say, how many meshes in this circuit? And people usually get this one right. There's 2. Okay, so let's label them. And I usually have you pick clockwise or counterclockwise for each of them. You can mix and match all you want. Okay, and let's say this one is I2. I'm just kind of squeezing them in where I can, but what I'm saying is I1 goes around here in the clockwise direction, and I2 goes in the clockwise direction around there. Okay, so we have our mesh currents labeled. to be a good engineer, you need good habits. Well, one of my habits to get all of my signs correct is then to label polarities on my passive components. Okay, so, and I'm going to do it for each mesh because it's going to differ depending on which mesh we're writing the KVL for. So I'm going to take I1 and I'm going to label polarities, and I'm going to label it inside the mesh. And when I write the KVL for I1, I'm going to use the polarities that I wrote inside the mesh. Okay, so let's do that. I1 is going to flow this way. That's active. That's always going to be plus on top, minus on bottom. I1 is going to flow to the right through R1, and that tells me, according to the passive sign convention, that it's going to be plus on the left and minus on the right. It's then going to take a right turn and go down through R2. So that is going to tell me that it is plus on top and minus on the bottom. That all comes from the passive sign convention. Positive current flows from high potential to low potential. So the positive side to the negative side. Okay, so that one's all set, right? We're back to where we started. We've labeled everything there. Let's go do the same thing for I2, and it's going to be a little different in some places. Okay, so I2 is going to start here, and it's going to flow up, and here's where it's different. And this is why I'm labeling it inside the mesh, so that I can use those when I write the KVLs. Okay, it's going to flow left to right, and it's going to flow top to bottom. Okay, if you write those, it's going to help you get the signs right. It's going to help you get the signs right when you write the KVLs. Okay, so it's a good habit to get into. So label your mesh currents, mark your polarities for the passive elements, which I didn't even have in there. Now you're smarter than the cutout text that I put in there. Anyhow. All right, write two KVLs. We're not always going to write KVLs, but for this problem and starting out, we're going to write KVLs. It's the default equation of mesh analysis. When in doubt, write a KVL. But there's reasons to write other types of equations, and we'll look at those in future videos. Okay, so I'm going to write a KVL for the I1 mesh. And I'm going to stay symbolic for now. When we get comfortable with everything, we can start to skip this step, but I want to stay symbolic as much as possible. So I'm going to start on the lower left, as is my habit, and I'm going to go clockwise. So we're going up across the 21 volt, right? It's negative on the low bar, positive on the negative on the small bar, positive on the long bar. So we're going up. So it's going to go up VS. As I move from here to here, I'm going down. Let's call that VR1, the voltage across R1, and it matches this polarity. And then I'm going down across R2, so that's VR2, down across it, and it's VR2. And we're back to where we started, right? Same node that we started on. So that's equal to 0. Okay, so I think we're in good shape with that one. Let's do the same thing. I'm going to put it, it's going to be right here, and let's do the same thing for I2. So we're going to write a KVL around I2. Okay, I'm going to start here, and I'm going to work my way around clockwise. So moving from the bottom to the top of R2, it's going to be a drop, right? I'm using the red polarities now. So I'm dropping across R2, so that's going to be VR2, and then I'm going to drop across R3, so that's VR3, and then I'm going to drop across R4, and I'm back to where I started, so that's equal to 0. Okay, maybe I could label those two. This is VR1, VR2, VR2, VR3, and VR4. All right, next step, step 3. We are going to use Ohm's law to write expressions for these voltages, and where applicable for the passive elements, and we're going to plug those in. Okay, so I'm going to come over here. Vs is equal to 21. That's a constant. It's an independent voltage supply. So Vs is equal to 21 volts. Okay, that one's boring. That was our only active element in this circuit. Okay, VR1. Think back. Is it just the previous video? I think it was just the directly previous video. How do we find that voltage based on the mesh currents? Okay, VR1 is equal to, okay, well, according to that plus and minus, the positive current direction is going to be left to right. Okay, and then we multiply it by the resistance. So does I1 touch that current? Yes, it does, and it flows in the same direction. So it's going to be positive I1. And does I2 touch it? Nope, so it's not in the expression. And then we just take that current and multiply it by R1. Okay, you see why I had you do those exercises before, hopefully. And that's what we're going to ultimately plug in for VR1. We're going to do the same thing for VR2. Okay, now the polarities differ depending on which KVL you're writing. Okay, right now, plus to minus in the orange is going to give me a current direction, a positive current direction of down, okay, according to the passive sign convention. So does I1 touch that current? Yep, and it goes in the same direction. Does I2 touch that current? Yep, and it goes in the opposite direction. And then I multiply by R2. Okay? So we have all of those voltages expressed in terms of our unknowns. Ultimately, what we're going for is a system of equations that has a bunch of constants, and we know R1 and we know R2 and we know Vs. So we have, those are our constants, and we only have unknowns. So we want a bunch of numbers and we want our unknowns and nothing else. That's the goal here. And I think we're just about ready to do that. So use Ohm's law to express the resistor voltages in terms of the mesh currents. Okay, now all we got to do is plug them in. So Vs, I'm going to stay symbolic for now. Vs is equal to, oh, nope. No, I'm copying this. Copy that and plug in all of this stuff. So Vs comes down, the minus comes down. Okay, and then I plug in what I have over here. So this is going to be I1, R1. Okay, this minus comes down, and I plug in whatever I have here, I1 minus I2, R2, and that's equal to 0. Okay, looking better. Not quite there, but looking a lot better. I'm pretty happy about that one. Okay. Coming over here and playing the same game. Now we're using the red polarities. Okay, so I have to, VR2 is going to be different in this case. And I've got to say, according to the red polarity, the positive current direction is going to be up. Okay, so VR2 is equal to, well, does I1 touch it? Yes. But now it flows in the negative direction, negative I1. Does I2 touch it? Yes. And it flows in the positive direction. And we multiply by R2. VR3. See if I can squeeze that onto the screen. VR3, okay, positive current direction is to the right, plus and minus through a passive component to the right. Does I1 touch it? Nope. Does I2 touch it? Yep, and it's in the positive direction. And we multiply by R3. This becomes a little bit of a bookkeeping exercise. You gotta, that's I2, that's R3. Careful with your subscripts there. Okay, last one for these voltages are for VR4. Let's see, plus up there, minus there. It's going to flow down. Okay, does I1 touch it? Nope. Does I2 touch it? Yep. And it flows in the positive direction. So there's I2, and this one's R4. So I have those three voltages expressed in terms of the mesh currents. I just got to plug them in. So I'm going to take this equation, and I'm going to rewrite it here, substituting where necessary. So this negative sign is going to come down. I get negative I1 plus I2, and I multiply by R2. This negative sign comes down. I2, R3. This negative sign comes down. I2 R4, and that's equal to 0. Oh, it's behind me. Ready? Whoop, whoop. There it is. Okay, so we're doing pretty well. We have two unknowns. We want to find I1 and we want to find I2, and we have two equations, and they're in terms of those unknowns, so that's pretty good. What's left for us to do is put them in a format that allows us to solve them. So step 4 up here, scrolling back up, go up. Whoop. Whoa, what just happened there? I've never rotated like that. Is everything crooked to you? Looks crooked to me. Cool. I don't know how to fix that. Hold on one second. I gotta pause the video. That was bizarre. Well, I found a new combination of mouse keys, mouse buttons that do fun things. Okay, so we've got to distribute and group like terms. All right, so we want to gather up all the constants that are in front of our unknowns as best we can. So I'm going to distribute each of, let's see, it's really just this one here. And if we have a negative sign, we've got to watch that as well. And then we're going to group them so that we have coefficients in front of our unknowns. And we'll get it into matrix form. I want you to watch those other videos on how to get from matrix form to the solution, because I think that's going to be important for you. Use the tool, practice. Use the tool that you're going to use to solve these in context when you need to solve them on an exam, at work, whatever is going to work for you. That's up to you. Okay, so let's see, VS. This one doesn't need to be distribute, I1, R1. I've got this negative sign here and R2 that's going to distribute to both of these. Okay, so we're going to have negative I1, R2, and we're going to have positive I2, R2, and that's equal to 0. Okay, grouping like terms, I'm looking for things that are in front of I1. So let's see, I have a term here that has I1, and I have a term here that has I1. So I'm going to start with those, and I'm going to say, I'm going to pull the negative and the R1 out. Okay, negative R1, and I'm going to pull this out too, negative R2. Okay, and that's all in front of I1. Okay, if I were to distribute the I1 back in there, I would end up with these two terms. Okay, I have only one term that has R2. Okay, and I'm just going to switch the order here because we start thinking about the resistors as coefficients of the unknowns. So commutativity allows me to do that. Okay, so I have all of my terms, all one of them, for I2 grouped together correctly. The other thing that I'm going to do is move the constants over to the right-hand side of the equation. So I have VS over here, and I need to subtract it from both sides of the equation so that I get VS like that. Okay, so that's the format that we're going for. We have one term for I1 with a bunch of coefficients. We have one term for I2 with a bunch of coefficients, and all of our constants are on the right-hand side of the equation. Let's go do it for, oh, this isn't an equation, is it? What did I forget? I would have taken points off. I forgot to bring down 0. That's equal to 0. Okay, but we're going to play the same game here. I need a little more headroom up here. And we're going to distribute this negative and the R2. Okay, so we're going to get positive R2 I1 and negative R2 I2 and negative R3. I'm flipping them around, but this term just becomes that term if I flip them around, and negative R4 I2, and that's equal to 0. Grouping like terms again, here's the only term with I1, so that's just going to get copied down. There's nothing fancy to do there. Here's my habit on this one, and I have habits, and I like them. I always write a plus and a parenthesis, and then I start pulling in the other terms. So if this has a negative, I'm going to pull it in here. It prevents me from making a sign error. And if you give me the negative result, it's the opposite answer. Okay, it's like the most wrong that you could be if you just have a sign error. Okay, so we have 3 terms that have I2 in them, and this one is negative R2, negative R3, and negative R4, and that's all in front of I2. Okay, check yourself. Go distribute that back out, and you're going to see that you get those three terms, and that's equal to 0. Okay, now it's in the same form, right? We have one term for I1, we have one term for I2, and all the constants, there are none because there were no supplies in this mesh, all the constants are on the right hand side. From here, we plug in values. Okay, so let's see, 21, let me see, oh, I have it up here. Okay, so hopefully you're looking at the image because I post these images for you, and I can do the plugging in by looking at my notes up here. So we get negative R1 is negative 6, and negative R2 is negative 24. So we're going to have negative 30 I1, okay, plus R2 is 24, and that's going to be equal to negative 21. Okay, now this 30 was a combination of resistances, right? So that's ohms and amps, and ohms and amps. We got volts over here, so everything is volts. So it is a KVL, it's a summation of voltages still. So that one looks good to me. Let's go do I2. Okay, so R2 is 24, that's in front of I1, and then we've got negative R2, R3, and R4, so that looks like it's going to be negative 48 I2, and that's equal to 0. Okay, so a lot of times when I'm writing these on the board, and I'll certainly do it in our live problem sessions, these are the equations that form the system of equations. I have two unknowns, and I have two equations, and now we just need to solve them. So if you watched the video, it's kind of a little detour path on solving systems of equations with matrices, then you know we're going to take these two equations and we're going to put them in matrix form. Okay, we'll go orange here for now, and I'm going to take the coefficients of I1, and it's going to be negative 30. The coefficient of I2 is 24. All right, and we're going to multiply this by our vector of unknowns, I1 and I2, okay, and it's going to be equal to whatever's on the right hand side. Okay, so this is going to be negative 21. I'm going to play the same game over here. I'm going to say this equation fills in this row of the system of equations here. So the coefficient of I1 is 24. The coefficient of I2 is negative 48. And the right hand side, the constant, is 0. Okay, so a lot of times to save board space, pixel space, things I love about teaching on video, my whiteboard markers never run out. I'm enjoying that. Okay, but to save a little room and to kind of mimic how we're going to solve this, a lot of times I'll write this in a different form, because we're going to invert this matrix. Okay, it is important to write the negative 1 because we're going to invert that matrix, and we get negative 30, 24, 24, and negative 48. Okay, and then we're going to multiply it by the right hand side. Negative 21 and 0. And that's going to equal our vector of unknowns. So we're just solving that system for our vector of unknowns. And really it's mathematically correct. It's drawn a little differently than some people do. But that lets me write the answers in here. So I1 and I2 are going to equal the values that we put in here. So I'd encourage you to try to solve this system yourself. I need to find a calculator. Okay, I have my old trusty 85 here. Which nobody seems to own anymore, but I still love the thing. I bought it in 1993. It's been around the world with me and back, and it works great. it works great because I've practiced with it for years, and I've gotten to the point where I trust the answers when I enter them. I still think about them and make sure they're in the ballpark correct, but practice with your tool. Okay, so the solution I get for this is 1.167 amps for I1. For I2, I guess I could still use red here, although I think it's becoming less necessary, is 583.3 milliamps. Okay, hey, I got I1 and I got I2. Oops. And we're in good shape there. Okay, so now we have our mesh currents. This video is getting long. Sorry. They're going to get longer. We have our mesh currents. What are we doing with them? We got to find VA. Okay, VA is the voltage at this node with respect to ground. So I'm going to throw out these polarities. Okay, I can give you a fresh copy down here too. Okay, I usually don't draw it over. I usually just look at the original schematic, but just so that it doesn't get too cluttered for your notes here, VA is here. I'm not thinking about the polarity from I1. I'm not thinking about the polarity from I2. I'm thinking about the polarity as it's labeled in the original problem. And this says find VA with respect to ground when we only have one subscript. It's the voltage at this point with respect to ground. That's the polarity I'm going to use. So if I want to find VA, I say VA is equal to, well, the positive current direction according to that polarity is down. And I say, does I1 touch it? Yes, it does. And it flows in the positive direction. And does I2 touch it? Yes, it does, but it flows in the opposite direction, so it's negative. And then we multiply by R2. And there's our voltage. Now we know I1 and I2, and we know R2 from the problem, so we just have to plug things in here, right? So VA equals 1.167 amps minus 583.3 milliamps. Pay attention to those prefixes. We're going to multiply by 24 ohms, and let's see what that looks like. I can grab the calculator for this one, and I'll do it on screen. Okay, and apparently when I start the program, it starts with fresh as a daisy RAM, as if I just put in batteries or reset it. So let's see how that looks. So you get to watch me put it in engineering mode. Okay, the only mode that's worth anything. Okay, 1.167 amps, so no exponent needed on that one, minus 583.3 e negative 3, since that's in milliamps. Now be careful, don't just multiply by 24. Think of your order of operations. Okay, I'm just going to hit enter on that and get the current, and then multiply it by 24. And that's going to give me, ooh, a little bit of rounding. Ooh, exciting. Who doesn't love error? But that ends up being 14 volts. Okay, 14 volts. Isn't that what we found using the seat of the pants method? It is. Whew. Holy cow, that was a long road, wasn't it? Why in the world would I do this? The seat of the pants method was so much faster. Here's why. Seat of the pants method isn't going to work for more complicated circuits. Mesh analysis is. This scales. I can make this circuit bigger. I can apply the same principles. And if I practice, I can do it much quicker. This was our first time walking through it. But we end up at the same place. The other benefit is, hey, if I want to go find the voltage across R4, all I got to do is take I2, which I already know, and multiply it by R4. Okay, so that's going to be 5.83 volts. See how quickly I can do that. Okay, so if I know the mesh currents, I know everything I need to know about what's going on in this circuit. It's really a powerful way to do analysis. It's organized, and we can consistently get to the right result. Okay, You're not good at it yet. You got to practice it, and you got to watch a lot more examples. So we're going to do another example in the next video, and I'm going to call it there because it's a half hour. I'm sorry. Okay, stay tuned and good luck, folks.